This is problem number 6 from section 310. In this problem it says, suppose that a drop of mist is a perfect sphere and that through condensation the drop picks up moisture at a rate proportional to its surface area. So, proportional to its surface area. Show that under these circumstances the drop's radius increases at a constant rate. So they want to know, does dr over dt increase at a constant rate? So the first thing we need to do is we need to start with the formulas. So we know that the volume for a sphere, and you might have to look this up, but it's 4/3 pi r cubed. And we know that the surface area is S equals pi r squared. And this is kind of like a proof, really. We're going to go through and we're going to use these and we're going to manipulate them with algebra to show that basically dr over dt is going to be a constant. So suppose that a drop of mist is a perfect sphere and that through condensation the drop picks up moisture at a rate proportional to its surface area. So it picks up moisture at a rate proportional to its surface area. If it's picking up moisture, then that's dV over dt. So dV over dt, what they're telling us in this problem is that dV over dt, because when you pick up moisture, you're increasing your volume, is proportional to its surface area. Well, proportional means that you take the surface area times some constant, which is K. So they're telling us in this problem that the volume is changing, the rate of the volume changing is equal to some constant times the surface area. That's the proportional thing. We've seen this in pre-calculus before. We take K times some number or some variable, and that's how this and the two pieces are changing proportionally. So what do we need to do? Well, we don't have dV over dt, so we need to find that by taking the derivative here. So let's go d over dt of v equals 4/3 pi r cubed. When we do the derivative of this will be dv over dt equals, and this will be, bring the 3 at the front, 3 times 4/3 is just 4 pi r squared, but we're doing the implicit, so it's dr over dt. Now this should immediately look familiar. Oop, I wrote that down wrong. It's not pi r squared, that's the area for a circle. Sphere is 4 pi r squared. That was my bad. So this should look very similar to the surface area. The only difference is we have this rate of the radius changing here, this piece. Well, let's see how all this fits together. dV over dt is equal to this, so using substitution I can plug 4 pi r squared dr over dt here. So that'll be 4 pi r squared dr over dt is equal to K times S. But S stands for the surface area, and that's 4 pi r squared, so I can say 4 pi r squared dr over dt is actually equal to K times 4 pi r squared. But now I have 4 pi r squared on each side, so I can just divide that across, and it'll cancel, and I get the rate of change for the radius equaling this constant K. That's a constant. So it says, show that under these circumstances the drop's radius increases at a constant rate. We just proved it by taking the derivative of the volume and plugging that into our proportional equation dV over dt equals Ks.